Today we're going to be talking about systems of linear equations and inequalities. This is hopefully a topic that you've seen a little bit before in your previous coursework, in particular intermediate algebra, but if not, we'll still be going in full depth today, both in terms of what you have hopefully previously seen and some new concepts such as how to deal with a system of linear equations with three unknowns. So without further ado, let's go ahead and get started. So first of all, just definition-wise, a system of equations just means you have at least two equations, if not more, where you're solving for all their unknowns. So this first one is probably what you're most familiar with. That would be a system of two linear equations. Both of these are lines. The second one might be something that you've seen before, which would be a system of two nonlinear equations. So while the second equation is linear, the first one is not. We're not going to go too far in depth with this, but if you ever encounter something like this out in the wild, I would actually just recommend graphing both and then seeing where they intersect is really the best way to handle such situations, although there are other techniques you can use as well. The last one that we will actually be going over today is if you have a system of three linear equations. So the way that these variables still relate to one another is considered linear. We don't have any squares going on. We don't have any exponents going on. We don't have any rational functions going on. They're all linear, but then we're now dealing with three dimensions. So that will be a new element that we introduce today. As a spoiler on what those three dimensions look like, if I have an x-axis and a y-axis, the z-axis is actually coming off the page, if you can visualize that way. So picture another axis. Oh, and I just also labeled x and y backwards. Oh my lord. Why did nobody stop me? We have a y-axis going straight up and down, an x-axis going straight across, and the z-axis is coming straight out the page. So that's how you visualize those three different axes. So you should think of the z-axis as out of the page. And just like usual, the y-axis is straight up and down, and the x-axis is straight across. If something is a solution to a system of equations, that means that it is a point that works for all of the equations in your system. So if it's a system of two equations with two unknowns, it is a point that works with both equations. A system of three equations with three unknowns is a system that works with all three equations. Hypothetically, you could have as many unknowns as you could possibly imagine. You could have infinitely many unknowns. That gets into like way higher level math than is the scope of this class. We're going to stick with about three unknowns, but you can have as many variables as you want to solve for, possibly. If the system of equations has at least one solution, it's called consistent. So previously in the past, you would have just said either one solution or oftentimes infinitely many solutions. Infinitely, there we go, many solutions. Here we have a specific vocabulary word that deals with both of those scenarios. That's considered to be consistent. It makes sense. And we're also going to take it one step further. When we're talking about infinitely many solutions, we're going to describe how we have infinitely many solutions. If there is no solution, the more sophisticated word that we can use for that is calling it inconsistent. It means that the results don't make sense. And again, it's considered to be linear whenever you just have a constant being multiplied by an x, and then they're kind of labeling instead of calling it y, they're calling it x2 kind of down there. That notation is not important per se. Really just know that you could have as many unknowns as you could possibly imagine. It doesn't have to be restricted to just three like we're looking at today. But let's go into some more concrete examples here. So how do you check if something works as a solution to a system of equations? Well, you actually just plug in the points. So it might be helpful to sort of label. We've got our x, we've got our y. So this is a situation we just have straight up and down y, straight across x. And then we could just plug in the point to make sure that it works with both. So for the first equation, we're replacing x with 2, y with -1. And we're going to see if that's true. So 4 times 2 gets us 8. Minus a -1 is the same thing as adding 1. And 8 plus 1 does indeed equal 9. To check the second equation, we did the same thing. So we plug in 2 for x, we plug in -1 for y, and we check if that's true. So 6 times 2 gives us 12, 5 times negative 1 gets us minus 5. 12 minus 5 is indeed 7. So we are good. Now this is getting at the idea that we can throw on that other dimension. So if straight up and down is y, straight across is x, out of the page is z. So that's the new thing, that z is coming out of the page. Or the screen if you're doing this entirely electronically. It's what allows us to model three-dimensional objects. So a lot of times engineers and scientists will actually oftentimes use 3 dimensions all the time because most things actually are 3-dimensional. We just tend not to, in kind of introductory math, overly complicate things with introducing that 3rd dimension just yet. But if you anticipate having to use math in your career, if you're any sort of scientist, any sort of engineer, if you're a computer scientist, you're going to be having to apply the 3rd dimension all the time. So it's a notation that's a good idea to get familiar with sooner rather than later. But the techniques are all the same. So if, for example, I wanted to check if this system of x equals negative z plus 2 and y equals negative 3x plus 3 and z able to be any real number works for these points, we want to plug them in and check if they work. So this in particular is actually an example where technically we have infinitely many solutions since we're allowing z to be any number, and then we plug it in to solve for x, and then we plug in that x to solve for y. We are technically allowing infinitely many solutions, but there's a specific format that we're allowing infinitely many solutions. It's not the case that infinitely many solutions means anything works. It just means I could not possibly count all the different solutions that exist here. So let's see how that looks in practice. So all of these points are listed x, y, z. So in particular in this first point, negative 1 is our x, 6 is our y, and 3 is our z. So we're going to plug in negative 1 for x, plug in 3 for z, and for the first equation there is no y term. We check if negative 1 is equal to negative 3 plus 2. It is. It works for the first equation, but remember for a system it has to work for all the equations in the system. So let's check the second one. So we're plugging in negative 6 for y, we're plugging in negative 1 for x, negative 3 times negative 1 is positive 3. And negative 6 is not the same thing as 3 plus 3. 3 plus 3 is positive 6. That does not work, so that is not a solution. Now we want to try the next one. So I'm going to encourage you to actually go ahead and pause your video and try out each of these solutions in the system to see if they work. So for the second equation, it's again going to be helpful to label x, y, and z. In this case, x is 2, z is 0, negative 1 times 0 is still just 0. 2 does indeed equal 0 plus 2, so we're good there. And then for the second equation, we're plugging in negative 3 for y, we're plugging in positive 2 for x, negative 3 times positive 2 is negative 6, and negative 3 is indeed equal to negative 6 plus 3. So that one does work. And then let's just check the other ones for good measure. So again, we've got an x, a y, and a z. So we're going to check is 1 equal to 0, since negative 1 times 0 is still just 0, plus 2. It does not equal that. So we can actually even just stop checking at that point, because as soon as it doesn't work for one equation in the system, it doesn't work overall. And then for the last one, we want to check the same thing. So we're plugging in 0 for x. We're plugging in, it looks like 3 for z. 0 does not equal negative 3 plus 2. So we can just stop there. So the only one that works is B. Of course, we don't want to just always be guessing and checking, right? We want to actually be able to systematically talk about the solutions to systems of equations and find them. So when we're dealing with a system of 2 equations with 2 unknowns, there's really physically only 3 different things that can happen. We could have one solution, which means that I have 2 lines that intersect and they cross exactly at that x, y single solution. Whenever I'm solving, that means I get x equals a number and y equals a number, and I call it a day. The other way I can have consistent solutions in a system of 2 equations with 2 unknowns is that we could be talking about identical lines, which means infinitely many solutions. Which means I've essentially just rearranged the equation to be the same line listed twice. So an example of that might be if I have y is equal to x plus 2 and y minus x is equal to 2, all I did was subtract over x and I gave you the same equation twice. So that's the other way you can have consistent equations. The way that you would have inconsistent, also known as no solution, would be if I had two parallel lines. Now the way you tell algebraically in solving is if it's inconsistent, at some point you're going to get some nonsense like 0 equals 2, where all of your x's and all of your y's have disappeared, and you're left with a statement like 0 equals 2 that is false. The way that you will tell that there is identical lines is that at the end of your solving, you'll get something like 0 equals 0. So all of your x's will disappear, all of your y's will disappear, and you'll just be left with a statement that actually is true, such as 0 equals 0, 2 equals 2, something along those lines. When we're talking about identical solutions, we're going to be a little bit more sophisticated and not just say infinitely many solutions, but we're actually going to give the equation that is those infinitely many solutions. If there's no solution, then you can just stop there because there's no other way to elaborate further. And that's exactly what this is just stating in words. So there's two basic methods to solve a system of equations for two unknowns. Well, there's actually three. You could graph them, but let's say you weren't graphing them. And then what you would want to do is you either want to use substitution or you want to use elimination. Now I will say that once you get beyond two equations with two unknowns, elimination is actually the more superior method. And in particular, when next time we're going to talk about matrices, those use elimination. So being really familiar with elimination is important, but there are certain situations where just substitution makes more sense. Substitution is a lot of times how we really conceive of having to solve systems of equations, and maybe makes a little more intuitive sense of just how people tend to think. Not all people, but some people. So we're going to talk about both. So for substitution, your first step is to get either x or y by itself in one equation. So let's just arbitrarily pick the first one. So if I have 4x minus y is equal to 7, first of all, to me, it seems like it would be easier to get y by itself. And in particular, I'm going to subtract 4x from both sides first. 4x minus 4x makes 0. Negative y is equal to negative 4x plus 7. And then I want to divide all three terms by negative 1 to undo multiplying y by negative 1. And I get y is equal to 4x minus 7. Then you want to plug in this result into the other equation. So in particular, when we have 4x plus 3y is equal to 30, well, we just found out that since y is equal to 4x minus 7, I can replace y with 4x minus 7 in the other equation, and then I'm just going to keep the rest of it identical. So we still have the 5x, we're still multiplying y by 3, and that's still being set equal to 30. Now you want to solve for x, so I would first distribute the 3 to both of these terms, so I get 5x plus 12x minus 21 is equal to 30. Then I would want to combine like terms within one side of an equation, so that would be 17x minus 21 is equal to 30. Now I want to get x by itself, and I'm starting to run out of room here, so I'm going to just rewrite this up here. So I want to undo any subtraction, so I want to add 21 to both sides to get rid of subtracting 21. I get 17x is equal to 51. And as a final step, I want to undo multiplying by 17 by dividing by 17. So x is equal to, I believe that is 3, although just for good measure, I'm going to start having a calculator ready here because we might be dealing with some bigger numbers here soon. So that would be 51 divided by 17 is indeed positive 3. But we're not done yet because we need a solution for both x and y. And thankfully, we already have a statement for y in terms of x. So now we're going to plug in to find y. So y is equal to 4x minus 7. I just found out that x is equal to 3. 4 times 3 is 12, so y is equal to 5. So I just found out that my entire solution is the point 3, 5, because x is equal to 3, y is equal to 5. Now let's talk about how elimination will work, since a lot of times that is used. So you want to first pick a variable you want to eliminate, which means you need to figure out something you would multiply an equation by, such that when you add it to the other equation, it's going to undo each other. So in particular here, if I picked the y's, I need to figure out what would I multiply negative y by, such that when I added it to 3y, it made 0. Well, 3 plus negative 3 is 0, and negative 1 times positive 3 is negative 3. So in order to make the first equation look like negative 3, I'm going to multiply it by 3, which of course I just erased way more than I intended to there. Just wanted to get rid of that underlining. So you need to multiply that first equation by 3 so that when you add it to the second equation, it will cancel out, so to speak, that negative 3y plus 3y makes 0. So I distribute to the first term, that's 12x. Distribute to the second term, that's negative 3y. And distribute to the last term, that's 21. The other equation, I'm just going to rewrite. Now, had it not been obvious how you could have canceled them out, it would have also worked to multiply them by the coefficient in front of each other, so to speak. So like, let's say I wanted to eliminate the x's instead. What I might have picked was multiplying the first equation by 5, the second equation by 4, and then just flip the sign on one of them, maybe the second equation, and then I would have 20x minus 20x. That is also a method that works. I like to try to keep the numbers small when I can. So let's go ahead and add this straight down. So 12x plus 5x makes 17x. Negative 3y plus 3y makes 0, just like I designed. 21 plus 30 gives us 51. Now we're down to the final step of dividing by 17. X is equal to 3. And then you still have to plug that into one of your equations. It doesn't matter which one. Let's just say you picked the first one. So you would plug in 3 for x to solve for y. So we get 12 minus y is 7. Subtract 12, subtract 12. Negative y is negative 5. Divide by negative 1, divide by negative 1. Y is equal to 5. So your point would still be 3, 5, solving that way as well. You are allowed to pick whichever method you prefer, but just again as a warning, elimination when we get more complicated systems than 2 equations and 2 unknowns is going to be the better method for reducing user error. I want to go ahead and encourage you to pause your video and go ahead and solve this system of equations. From here on out, I'm going to use elimination consistently, but you can always still do substitution if you prefer. So here, if I wanted to eliminate, let's say I want to eliminate my x's this time. I believe I would multiply the first equation by negative 2 so that negative 4x plus 4x makes 0. So I distribute to all 3 terms. That gets us negative 4x minus 2y is equal to negative 10. And then I'm just going to rewrite the second equation. And here something special happens because negative 4x plus x is 0. Negative 2y plus 2y is 0. So I'm left with 0 equals negative 2. What type of situation is that? That's going to be no solution because that's a statement that is just simply false and there are no x's left. Let's try this one. So again, go ahead and pause your video and try to solve this yourself, and then let's compare. So here, if I want to use elimination on, let's say, the y's this time, well, I have 1y and I want to add it to negative 3y to make it add to 0. So I want to multiply that first equation by 3. 3 times 2x gets us 6x. 3 times 1y gets us 3y. 3 times 4 gets us 12. And then I want to rewrite the second equation. Here, 6x minus 6x makes 0. 3y minus 3y makes 0. And 12 minus 12 makes 0. So this is an infinitely many solutions situation. Infinitely many solutions. But we want to be more precise. So we're going to say it's consistent. And we're going to say where the solution is. So 2x plus y is equal to 4. We may just want to rewrite this in y equals mx plus b. So I would take away 2x from both sides. Y is equal to negative 2x plus 4. Both of those equations are simply rearranging that equation, and that is the line that both of these equations are on. Now let's talk about a system of 3 equations with 3 variables. And in particular, here I gave 2 pages because it's just going to be a lot more writing. This is where elimination is nice. So you want to somehow use all 3 equations twice in order to eliminate one of your variables. I'm going to pick the z variable to eliminate. You don't have to do that one, but that's going to be my goal. So first, I'm going to combine a and b to eliminate z. And then I'll do the same thing with a and c. You could do a and b and c. You could do c and b and c and a. Whatever, however you want to conceptualize it, that's fine. I just noticed that a already, all the coefficients are just 1 or negative 1. So it seems like the easiest equation to work with in order to start eliminating. So for our first equation, a, that's x plus y minus z is negative 1. The second equation, b, is 4x minus 3y plus 2z is 16. So the thing I would have to multiply the first equation by to eliminate the z's would be 2. So 2 times x gets us 2x. 2 times y gets us 2y. 2 times negative z gets us negative 2z. 2 times negative 1 gets us negative 2. And then I'm just going to rewrite the second one. Now I'm going to add straight down. 2x plus 4x is 6x. 2y minus 3y makes negative y. Negative 2z plus 2z eliminates to make 0. Negative 2 plus 16 is 14. Now I'm going to do a similar process. Really what I'm actually doing here is I'm making a system of 2 equations and 2 unknowns so that I can solve something similar to what I did before. So now I'm going to combine a and c to eliminate z. You have to use each equation at least once, and there will be one equation, in this case equation a, that's used twice. So we have x plus y minus z is negative 1, and for c we have 2x minus 2y minus 3z is 5. So to eliminate z this time, I'm going to multiply the first equation by a negative 3, because you remember you want to be able to add them up and make that cancel out, so I need to change the sign on that z as well. So negative 3 times x gets us negative 3x, and I'm going to pause and actually just rewrite this below. I'm going to make you watch me do that. That is much better. We have more room to write now. So for the first one, again, we want to add something to negative 3z to make 0, so that would be positive 3, so I need to multiply negative 1 by negative 3 to make that happen. Negative 3 times x gets us negative 3x. Negative 3 times y gets us negative 3y. Negative 3 times negative z gets us positive 3z. Negative 3 times negative 1 gets us positive 3. And then I'm just going to rewrite the other equation right underneath. Negative 3x plus 2x gets us negative x. Negative 3y minus 2y gets us negative 5y. Positive 3z minus 3z makes 0. Positive 3 plus 5 makes 8. So we've really just combined these to make a new system of two equations with two unknowns to at least find our x and y, and then we can further work to find our z. So I'm just going to rewrite our system of two equations with two unknowns. And now here we want to solve for either x or y. We could again use elimination. So in particular, I noticed that, it probably is about the same amount of work to either eliminate x or y. I'm just going to pick eliminating x by multiplying the bottom equation by 6. So I'm going to rewrite our first equation. The bottom equation, 6 times negative x gets us negative 6x. 6 times negative 5y gets us minus 30y. 6 times 8 gets us 48. And now we're just going to add straight down. 6x minus 6x makes 0 by design. Negative y minus 30y gets us negative 31y. 14 plus 48, so 4 plus 8 gets us 2, carry the 1. 1 plus 1 plus 4 gets us 6. Then we're going to go ahead and divide by negative 31 so that we undo multiplying by negative 31. So y is equal to negative 2. And now I systematically plug back in order to find my other variables. So I'm going to first find x because I already have y and x in a single equation with each other. I could pick either equation. I'm just going to pick the second one. So we have negative x minus 5y is equal to 8. We want to plug in that negative 2 for y. Negative 5 times negative 2 is positive 10. Subtract 10 from both sides. Negative x is equal to negative 2. Divide by negative 1. X is equal to 2. Now we have to go back to the original in order to then solve for z. So I'm just going to pick the first equation. So we have x plus y minus z is negative 1. So we have x is 2, y is negative 2, minus z, and that was a negative 1. Right, it was negative 1. Yeah. 2 plus negative 2 is 0. Divide by negative 1 on both sides, so z is equal to positive 1. So our final solution is 2, comma negative 2, comma positive 1. This system of three equations with three unknowns is very similar. But the result is a little bit different, so I'm still going to kind of walk through it with you. However, I still want to encourage you to first pause the video and at least rearrange this to be a system of two equations with two unknowns on your own. All right, so here I'm going to combine first equations A and B to eliminate z. And what's really nice about those is they're actually already set up that way. There's actually no more work needed to eliminate z in that because negative z plus z already does make 0. So x plus 2x makes 3x. Negative 2y minus 3y makes negative 5y. Negative z plus z eliminates to make 0. And 8 plus 23 is 31. Now we need to somehow use equation C. I'm just going to choose to combine A and C. So we're going to combine A and C to eliminate Z. So equation A, x minus 2y minus z is 8. In C, that's 4x minus 5y plus 5z is 53. So we have to multiply the first equation by 5 to make that happen, since we want to add to positive 5z, and the first equation has a negative z. So 5 times x is 5x. 5 times negative 2y is negative 10y. 5 times negative z is negative 5z. And 5 times 8 is 40. And then we just rewrite the second equation. And now we're going to add straight down. 5x plus 4x makes 9x. Negative 10y minus 5y is negative 15y. Negative 5z plus 5z makes 0. 40 plus 53 makes 93. And so now we have a new system of two equations with two unknowns. We have 3x minus 5y equals 31. 9x minus 15y equals 93. Now we want to go ahead and solve for one of our variables. I'm just going to choose to deal with the x's. So I would have to multiply the first equation by negative 3. So negative 3 times 3x makes negative 9x. Negative 3 times negative 5y makes positive 15y. Negative 3 times 31, it gives us negative 93, and you're probably already noticing something very special is happening here. Because negative 9x plus 9x makes 0. Positive 15y minus 15y makes 0. Negative 93 plus 93 makes 0. So this is a special infinitely many solutions situation. But we're going to be more sophisticated, but then just noting infinitely many solutions, we want to talk about how there's infinitely many solutions. As if there was an unclean transition there. So to talk about how there are infinitely many solutions, let's really focus on these two equations where we just figured out that they were fancily rewriting the same equation. So both of these equations are reflecting the same thing. So we can go ahead and solve for y in one of these equations. Let y be the variable that we pick, and then we want to be able to write the other two variables in terms of y. So in this particular case, let's add 5y to both sides. 3x equals 5y plus 31. Then subtract 31 from both sides. My goal is to get y by itself, so 3x minus 31 is equal to 5y. And then you want to divide by 5 on all three sides. So y is equal to 3/5 x minus 31 over 5. So if we're talking about solutions right now, we have x, we have 3/5 x minus 31 over 5. And all we're missing is the z variable, so that we've rewritten everybody in terms of that z variable. So let's just pick that first equation to rewrite that z variable entirely in terms of x. I believe I misspoke earlier, so let me just go ahead and backtrack. By solving for y, I am choosing to rewrite everybody in terms of x. Had I solved for x, I would have chosen to rewrite everybody in terms of y. My goal is to rewrite all my variables just in terms of one variable. So if we focus in on that second equation, x minus 2y minus z is equal to 8. We also have something I can replace y with. Minus z is equal to 8. Then I can go ahead and get z by itself by adding z to both sides. So I have x minus, and I might want to distribute those two. 2 times 3/5 gives us negative 6/5 x. Negative 2 times negative 31 gets us positive 62/5 equals z plus 8. Then I want to subtract 8 from both sides. So x minus 6/5 x plus 62/5 minus 8 is equal to z. And if you're feeling a little bit lazy about that fraction manipulation as I am at this point in the video, totally fine to break out a calculator. Might want to make the calculator so that you can see it. So we have 1 minus 6/5 in terms of x's, so that should be negative 1/5. And then for the plain numbers, those constants, we have 62/5 minus 8. Or as a nice fraction, that would be 22/5. So our z, more neatly written, is negative 1/5 x. And then my memory is apparently of a goldfish. I already forgot the other one. 22/5 plus 22/5 is equal to z. So that's exactly what I write for the z variable. So we're able to talk about how there are infinitely many solutions by rewriting everybody in terms of the same variable. And most likely the numbers would turn out a little bit cleaner on a homework, but in theory you can always still manipulate fractions because fractions are indeed just numbers. So let's talk about systems of equations and inequalities by graphing. So we just went over algebraically how to solve. When we're talking about a system of two equations with two unknowns, we can also think about graphically speaking. If there's a single solution, it will be where they physically cross. If it's an inconsistent system, if there's no solutions, then they're going to be two parallel lines that never touch. And if it's a dependent system, infinitely many solutions. You can physically draw the line, and then you can create the equation for the line. Whenever you're talking about three equations with three unknowns, that does look a little bit different. In particular, it could be such that, if you have you could have infinitely many solutions in like different ways that the planes intersect at like multiple points, kind of like this, versus, no solution where they're just like three parallel lines on top of each other. So there's lots and lots of different ways to sort of visualize the different ways there can be infinitely many solutions when you're talking about physical planes like this. So this becomes much more difficult, as you can physically see, to do on something like a graphing calculator. You really want to solve that algebraically. There are more sophisticated softwares that allow you to sort of look at these visuals, but that's way beyond the scope of this class. When it comes to systems of inequalities, really the best way to solve them is graphically. So while system of inequalities with three unknowns do exist, or a system of nonlinear inequalities also exists, that's beyond the scope of this class. We're really not going to focus on those. What we're going to focus on are things that we could easily graph and shade to see what those solutions would be. In particular, you want to note, how do these systems of inequalities even just like work, right? So if I have x plus y equals 3, well, that is the line y is equal to negative x plus 3 if I subtract x from both sides. And if you had a less than sign, that means you physically shade below the line. That's why this stuff down here in the red is shaded. I'm just kind of highlighting it, especially if you can't really tell the difference in the color. Less than is shaded physically below the line. Or if it doesn't look physically below to you and you're like, oh my gosh, I always should mess up the shading, just pick a testing point. So for example, if we pick this testing point, -2, -2, I would plug in -2 for y, -2 for x. -2 is less than -1 times -2 is 2 plus 3. -2 is indeed less than 5. We're good. If you're greater than, then you shade physically above the line. Or you can always pick a testing point. Personally, I recommend doing both. I would recommend getting an intuition of what above and below the line look like, but then still pick a testing point to double check. So for example, this point over here, 4, 2, you plug in 2 for y, 4 for x. Is 2 greater than -1? It is. You're good. And that's exactly how you solve a system of linear inequalities, is you shade both lines according to both above and below and testing a point, and then wherever they overlap is your solution. So let's take a look at an example. So if we have y is less than or equal to -2x plus 4, so first of all I want to graph this line. So we have starting at +4, moving down to right 1, or up to left 1, down to right 1, down to right 1, down to right 1, down to right 1. And then because it's an or equal to sign, I'm going to shade him in. Meaning I'm going to draw it with a solid line. Had it just been a less than sign, I would have done a dotted line to represent I don't want solutions physically on the line itself. Since it says y is less than or equal to, I'm going to shade below the line. And I want to pick a testing point to double check. So let's say, I don't know, -5, 0. If I'm going to plug in that, I want to check is 0 less than or equal to -2 times -5 plus 4. Is 0 less than or equal to 10 plus 4? Is 0 less than or equal to 14? It is. We're good. Then we want to graph the other line. So we start off at the y-intercept of -3. Then we're moving up 1, right 2, up 1, right 2, up 1, right 2, down 1, left 2, down 1, left 2, down 1, left 2. And it also has an or equal to sign, so I'm going to shade him in. This has a greater than sign, so I'm going to shade above the line. Then I want to double check. A point in here also works for this one. So let's say even the same point. Is 0 greater than or equal to 1/2, -5 minus 3. 0 greater than or equal to -5/2 minus 3. So that's basically -2.5 minus 3. So 0 greater than or equal to -5.5. It is. We're good. So your final solution, which I'm just going to really highlight to emphasize, is in this quadrant. And on an exam, I would maybe even just point to this is your solution so that your professor doesn't think that you're wanting to include the ones where you were just kind of showing your work of where it worked for one inequality but not the other. This is the same idea. You just have to rearrange them first because they're currently not arranged in y equals mx plus b format. So for example, for x plus y is less than 4, I might subtract x first. Y is less than -x plus 4. So I'm going to start at 4, then move down 1, right 1, 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 and then up 1, left 1, up 1, left 1. And this one's going to stay dotted. Why does he stay dotted? He's a dotted line because this is strictly less than sign. And because he's less than, I'm going to shade underneath the line. And then I can pick a point to double check. Let's just even say 0, 0. So is 0 less than -1 times 0 plus 4? 0 less than 4? It is. We're good. Now we want to rearrange the other equation. X minus y is less than 5. I want to subtract x from both sides because my goal is to get y by itself. And then when I divide by -1, what do I have to remember to do? Flip the inequality. So we start at -5, and then we're moving up 1, right 1, 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 down 1, left 1. Why am I also going to dot this line? Because it is a strictly greater than sign, there is no or equal to. And here it is greater than, so I'm going to shade above, and then I might want to double check that same point. Is 0 greater than 0 minus 5? 0 greater than -5? It is. We're good. So our solution is this region here. And so any point inside that region works for our system of inequalities. As always, do be sure to take a look at your textbook if you want some further examples, and do be sure to ask your professor about it as well.